In this session, I'm primarily going to talk about another important measure of a data, just like measure of central tendency, which talks about the central value of a particular data. The measures of spread talk about the spread in the data, or in other words, they talk about the variability that is present in the data. They talk about the dispersion that is present in the data. These are different words. I call measures of variability, measures of dispersion, or measures of scatteredness that is present in the data. By how much extent the data is dispersed or spread about the mean or any other location mechanism. So by how much? See, I got one central value. Around this central value, what is the level of dispersion of each of the observations, each of the points of the data? What is the extent to which they are dispersed away from the mean? So again, we are having one single measure of computation of the spread. So a simpler way is, whatever is the measure, the higher is the spread. It's an indication that my data is heavily dispersed from the mean, right? Wide variation in the data is there. Whereas if the spread is much lower, we see that more and more the values are concentrated around the mean. That's a simple interpretation of any of the measures of spread. And here, some of the important measures of spread that I want to look at. One is the variance and standard deviation. Both are one and the same. Variance is just the square of the standard deviation. So if I measure one of them, the other is automatically known. So we will look at the measurement of standard deviation or the variance, which is one of the most important measures of the definition of the spread. Then we'll try to understand the moments, which are another way of measuring the spread in the data. Then some simple measures like range, and we'll also talk about the interquartile range, IQR. So these are the four different kinds of measures of spread we are going to look at. But out of these four, the most popular and the most commonly used measure of spread is the standard deviation itself. When I say standard deviation, I am using its square version also, which is the variance. So it is primarily talking about, on an average, right? On an average, by how much extent are each of the observations in my data, they are deviating from the mean on an average. So some of them would be deviating much lesser, some of them would be deviating much higher compared to the mean. So all I am trying to look at is, on an average, by how much extent are my observations deviating from the mean. So basically it's like this: if I have x1, x2, x3, so on, xn as my observations, I got my mean x bar as sum of all these xi's divided by n. Now what we do in case of finding out the standard deviation is, the first step, each observation I subtract the mean. Each observation I subtract the mean. So these are the deviations from the mean, right? These are the deviations from the mean. Okay, let's define it. So first I am finding out all the deviations from the mean. Then squaring them. So squares of deviations from the mean. Summing them. sum of squares of deviations from the mean and divide by n minus 1. This is primarily the average. Or sum of squares of deviations from the mean divided by n minus 1 is the definition of variance of my sample. The definition of the variance is you find out the sum of the squares of the deviations from the mean and you divide it by n minus 1. Let's take some simple data set. Let's take this simple data set containing 10 values. Right? These are the observations. Now I will find out the mean for this. So the mean for this is nothing but I add up all of them and divide by 10. Otherwise, I can even use the Excel formula. I am getting it as 13.2. Now, to find out the variance from each observation, I subtract the mean. So you look at it, if I am doing from each observation subtracting the mean, so these are what are the values that are coming out? From each observation, 17 minus 13.2, 3.8. 10 minus 13.2 minus 3.2. From each observation, I have subtracted the mean. Then each one of them, I have squared them. So 3.8 square is 14.44. Minus 3.2 square is 10.24. So I have squared each of them. Each observation subtracted the mean, squared, and then I will do the summation of them. The summation of their values is how much? This is the summation 89.6. And this number I have to divide by n minus 1 to get the variance. To get the variance, I divide this 89.6 by n minus 1, which is 9. So 9.95 will become the variance. I even have a direct formula in Excel which will give me the same. I have a variance called var.s, sample variance. Var.s is nothing but sample variance, which I can find out for this particular data. You see that it is coming out to 9.95 itself. This is the way it gets computed, whereas this is a direct formula. So I'm getting the sample variance. Generally, I denote it by s squared. Initially, I'll compute the sample variance, which is the s squared, and I take the positive square root of this variance. That I call as the standard deviation. So the square root of the variance is nothing but the standard deviation. So either I can use a direct formula of Excel where I see STDV and a sample standard deviation, right? Or I have used the variance formula. So take the square root of this particular variance to arrive at the standard deviation. So the standard deviation is around 3.155. So this is the definition of the standard deviation and the variance. So on an average for this data, I can say that my observations are on an average 3.15 units dispersed away from the mean. Right? That is the meaning of the standard deviation. Now, in some cases, okay, let's derive one more formula. What is that we are defining the variance as? Each xi, I subtract it from the mean, square it, sum all of them, and I divide by n minus 1. Now let's expand this. Okay, 1 by n minus 1 sigma, because this is of the form a minus b whole squared, I want to do it as sigma xi squared plus x bar squared, which is the mean squared, minus 2 times xi times x bar. Okay, 1 by n minus 1 times Okay, sigma xi squared is same. Now x bar squared is also fine. Now here I'll take the common out. 2x bar times sigma xi. Right? I'll write it something like this. 2x bar times sigma xi. Now this is where I could even talk about, okay, now let me break all of them separately. Sigma xi squared. Now sigma x bar squared, it's a constant, so it's just becoming x bar squared minus, right? I mean each x bar I am having n times, so this is becoming n x bar squared. So this also minus 2x bar. This also I can write it as n times x bar because the sum is nothing but average times the total value. So overall it is coming out as 1 by n minus 1 times sigma xi squared. This is n times x bar squared minus 2n times x bar squared. So it is becoming minus n times x bar squared. So I can either have this kind of a formula for computing the variance, or I can use this kind of a formula. Both the formulas should give me the same result. Now let's see whether they are giving that kind of result or not. Sigma xi squared. So I'll find out xi squareds first of all. So this is my xi. So I'll take the xi squared. Okay, so this is what I'm taking as the xi squared. So I want sigma xi squared. So this is my sigma xi squared 1832 minus n times x bar squared. So from this number, I have to subtract n is 10. 10 times x bar is this one, x bar squared. So I'm still getting 89.6. So I can very well find out my variance as 89.6 divided by n minus 1, which is 9. So my variance still comes like this, and the square root of that number is my standard deviation. So either of the formulas I should be comfortable with. In some cases, I may use this kind of a formula for computing the variance, and in some kind of a cases, I may want to use this kind of a formula. So I have to be comfortable with both of them for the computation of variance. And the square root of that particular number is nothing but the standard deviation. Now that we got some idea regarding the variance and the standard deviation, the next thing that we are looking at is the moments. The moments, we simply say the moment of an order k about the value alpha. It is nothing but each observation I subtract alpha from it and raise it to the power of k, add it for all the observations, and I divide it by n. This is what is the definition of the moment. So typically we define the moment as the kth order moment about alpha. Kth order moment about alpha is nothing but each observation, from each observation you subtract alpha, that particular value you raise it to the power of k, you add it across all the possible values, and you divide it by the total number of observations. That is what we call as the kth order moment about the value alpha. Now if you look at mean, put alpha equal to 0 and k equal to 1. What is this becoming? Xi minus 0 to the power 1 sigma 1 by n. So it is actually becoming 1 by n sigma xi. This is nothing but the mean. So we'll say mean is the first order moment about the origin where alpha is 0. Similarly, you put alpha is nothing but the sample mean, and k you put it as 2. all it is becoming xi minus x bar to the power 2 sigma 1 by n. Or here we are just saying 1 by n minus 1 for the definition of the variance. But you could see that variance is nothing but the second order moment about the mean. So whichever is the moment about the mean, we call it as the central moment. So second order movement, second order central movement is nothing but the variance. The only thing is divisor is not n, the divisor is n minus 1. Otherwise, it's a second order movement about the mean. So that is what we are typically calling as the moments. So you can put third order moment, fourth order moment. These are the different ones that are going to summarize the data or probably give you the different kinds of summary measures about the data. Different kinds of summary measures about the data are typically obtained through the moments per se. Then the next thing that we are going to look at here is the range. One of the simplest measures of dispersion that is present in the data. I'm only looking at the maximum value minus the minimum value. That is what I'm calling as a range. So with our example, if I want to see what is the maximum value in our example, it is 18 and the minimum value in our example is 10. So the range is nothing but the maximum value minus the minimum value coming out to 8. So that's a straightforward. Then the other important technique or a mechanism or a measure of dispersion is the interquartile range, otherwise called as the IQR. As good as the range, we are doing a subtraction only. But we are not taking only the extreme values. So if the extreme values change, the range is going to change quite drastically. And range is considering only two values, nothing else. So range is actually very heavily impacted by the extreme values or outliers present in the data. Right? Whereas in the interquartile range, I don't take the maximum and the minimum. I take the quartile 1 and the quartile 3. There I have taken maximum and minimum for a normal range. For interquartile range, I take the quartile 3 and the quartile 1. I subtract Q3 minus Q1 to get my interquartile range. So one thing is it's nowhere affected by the outliers. But I have to find out Q1 and Q3. See, we know the median already. Median is splitting your data into two halves, whereas quartiles are splitting your data into four parts. Q1, Q2, Q3 and Q4 is the full itself. So your data is divided like this. If this is what is your data in the ascending order, probably we are putting three cuts in the data, saying 25% of the observations should be below Q1. Another 25% of the observation should be between Q1 and Q2. So this is Q1, this is Q2, this is Q2. So another 25% of the observation should be between Q2 and Q3. And the remaining 25% of the observation should be above Q3. So this is how the Q1, this is how the quartile 1 and quartile 3 are computed. And if you really dig a little bit deeper to understand Q2, it is nothing but the median. Because 50% of the data are below this, 50% of the data are above this. So Q2 is nothing but the median. Q1 and Q3 are the other two values. So a quarter of the values are having a value lesser than Q1. quarter of them will have value above Q3, 50% of them will lie between Q1 and Q3. And just as a formula also, we know that the median is nothing but n plus 1 by 2th element. We can very well go with Q1 as n plus 1 by 4th element, and Q3 is nothing but n plus 1 by 4th element from the upper side, or probably 3 into n plus 1 by 4th element. 3n plus 3 by 4th element will come out to be your Q3. So you can very well find out, let's say for this data set itself, I want to find out, right, there are 10 elements. So I want to find out, so I'll arrange this data first in the ascending order. So I'm sorting it. I'm sorting this data in the ascending order. So this is the ascending order of the data. Then we are trying to find out n is 10. So n plus 1 by 4th element is nothing but 11 by 4th element, or 2.75th element. So I need to take the second element and the third element. Second element is this, third element is this. So second element is 10, third element is 11. But I want 2.75th element. So this is where I depend on interpolation. Right? Second element is 10, third element is 11. So the gap of 1 is creating a gap of 1 here. I need 2.75th element. So this is like 75% away from 2 and 25% away from 3. So I will take a value which is 75% away from 10, which is 10.75, and 25% away from 11. So the other way of doing this kind of interpolation is take the minimum one. Okay, I want 2.75th element. Go with the 2th element, whatever is the second element. Second element is 10 plus whatever is the gap that I want. 2.75 is what I want. So I'll go with 0.75 times whatever is the gap that is existing in the output, in the outcome values. The gap is 1. So this is what will come out as 10.75. So interpolation is giving me that 10.75 will be my Q1. So in this case, my Q1 will be 10.75. Even if I am trying to use a formula called quartile, right, I'm using a formula called quartile. Out of this particular data, I'm going with a first quartile. Okay, here it is taking, there are different formulas for quartiles. Sometimes instead of n plus 1 by 4, people take even n plus 2 by 4th element. So let's not confuse. So we can very well go with the n plus 1 by 4 itself. Then I want Q3. If I want Q3, I want 3 into n plus 4, 1 by 4th element. So 3 into 11 by 4, 33 by 4, making it 8.25th element. So I'll take the 8th element. 8th element is 16. 9th element is 17. Right? So 8th element is 16. 9th is 17. I want 8.25th. So I'll take 16 plus what is that extra that I want? 0.25th is what that I want. And I take the difference between these two, which is 1. So I'll get it as 16.25. So my Q3 will be 16.25. And then we talk about the interquartile range, which is nothing but the difference between Q3 and Q1. Instead of maximum minus minimum, the interquartile range simply computes the difference between the Q3 and Q1. Right? So this is a simple way of computing the interquartile range. First we compute Q1s, Q3s, and from there is what we compute the difference between those two, calling it as the interquartile range. So traditionally we see that these are the very common mechanisms that are used as a measure for dispersion or the spread in the data. Though there are various other measures, the very commonly used ones are the ones that I have discussed right now. Thanks a lot for listening to this session. Thank you very much.